In previous videos, we saw how we can calculate the cotangent of an angle x if we put it in a triangle where we know the sine and the cosine of one of its angles, say gamma, and we know the ratio of the sides around the angle gamma, so a divided by b. And the formula is cotangent of x equals a divided by b minus cosine gamma divided by sine of gamma. Now I'm going to show you a different way of finding the cotangent of x. Suppose your angle x is here, and suppose you know the values of the sine and the cosine of this angle gamma here. Now since this is gamma and this is x, this angle must be gamma minus x. And the trick here is to find the ratio sine of gamma minus x divided by sine of x. If you find this ratio, then you can also find the cotangent of x. Suppose that this expression equals k, and suppose we found the value of k. Then we can apply the formula for sine of gamma minus x, and we get that k equals sine of gamma cosine x minus cosine gamma sine x divided by sine of x. Now cosine x divided by sine x equals cotangent of x, and we can cancel out sine of x with sine of x. Then we get k equals sine of gamma cotangent x minus cosine gamma, which means that cotangent of x equals k plus cosine of gamma divided by sine of gamma. And that's how we can find the cotangent of x if we know the value of the sine of gamma minus x divided by sine of x. Here are two possible applications of this way of finding the cotangent of x. Suppose that you have to prove that this point, and this point lie on a straight line, and you know the sine and the cosine of this angle here. You can calculate the ratio of the sine of this red angle divided by the sine of this red angle, and prove that it equals to the ratio of the sine of this blue angle divided by the sine of this blue angle. If the two ratios are equal, it means that the cotangent of this small red angle equals the cotangent of this small blue angle, meaning that the two angles are equal, and therefore this point, and this point must lie on a straight line. Indeed, we know that if two angles have the same value for their cotangent, and the two angles are between 0 and 180 degrees, then the two angles must be equal. Another application may be if we're trying to prove that two lines are isogonal with respect to an angle. Suppose we have this angle, for which we know this value of the sine and the cosine of the large angle, and we need to prove that this line and this line are isogonal with respect to this angle, meaning that we need to prove that this small blue angle here equals this small red angle here, in which case we can prove that the sine of this angle divided by the sine of this angle equals the sine of this angle divided by the sine of this angle. From here, it would follow that the cotangent of this angle equals the cotangent of this angle, and therefore this angle equals this angle as desired. Here's the optional problem. We have a triangle. This is its incircle and this is its x-circle, and these lines are connecting the tangency points of the incircle and the x-circle together. We drop perpendicular from this tangency point to this line here, and we drop a perpendicular from this tangency point to this line right here. Then we connect the 2 feet of the perpendiculars with this vertex of the triangle, like that. We need to prove that the two blue dashed lines are isogonal with respect to this angle, or in other words, that this angle equals this angle. And here's the solution. Let's label the angles of the triangle by alpha, beta, and gamma, and let's call this angle x and this angle y, so we need to prove x equals y. We now know that this is equivalent to proving that sine of gamma minus x divided by sine of x equals sine of gamma minus y divided by sine of y. So essentially, this here is what we need to prove, which would lead us to the conclusion that cotangent of x equals cotangent of y, which would mean that x equals y. First thing we need to notice is since this line and this line are tangent lines to this circle and this circle, then we know that this length equals this length, and also this length here equals this length here. Let's call this segment M, this segment N, this segment P, and this segment Q. Then we can apply the law of sines for this triangle, and also for this triangle, and this triangle. And then we get that sine of gamma minus x divided by sine of x equals P divided by Q times this length divided by this length. But these two lengths are equal, and so we can ignore them. Therefore, sine of gamma minus x divided by sine of x equals P divided by Q. And similarly, sine of gamma minus y divided by sine of y equals N divided by M times this length divided by this length. But these two lengths are equal, so we can ignore them. And so sine of gamma minus y divided by sine of y equals N divided by M. And therefore, we need to prove that P divided by Q equals N divided by M. This allows us to delete the useless parts of the picture and focus our attention on proving that P divided by Q equals N divided by M. Now, if this angle is alpha, We know that this length equals this length, since these are tangent lines to this circle, and therefore this angle equals 90 minus alpha over 2. Similarly, since this here is an isosceles triangle with angle gamma, then this angle equals 90 minus gamma over 2. So in conclusion, this angle is 90 minus alpha over 2, and this angle here is 90 minus gamma over 2. We get the situation sketched right here. This angle is 90 minus alpha over 2, which corresponds to this angle. This angle is 90 minus gamma over 2, corresponding to this angle. So this angle must be alpha over 2 plus gamma over 2, such that the whole angle is 180 degrees. But we know that alpha over 2 plus gamma over 2 plus beta over 2 is 90 degrees, and therefore this angle is 90 minus beta over 2, which is this angle right here. And now, since this is 90 degrees, we get that this angle here is beta over 2. Similarly, we get that this angle here is alpha over 2. Now consider this isosceles triangle here. It is isosceles since this and this are tangent lines to this circle. We know that this angle is alpha, so this angle is 180 minus alpha, and therefore this angle equals alpha over 2. Now, since this here is an isosceles triangle where this angle is gamma, then this whole angle here must be 90 degrees minus gamma over 2, which equals alpha over 2 plus beta over 2, and therefore this angle must be beta over 2. Similarly, if this angle is beta, then this angle equals beta over 2, and since this whole angle is 90 minus gamma over 2, then this small angle must be alpha over 2. Now let's continue this line until it intersects this circle at this point. Then this here is a cyclic quadrilateral, for which if this angle is alpha over 2, then this angle is also alpha over 2, and if this is beta over 2, then this angle must also be beta over 2. And now consider this triangle and this triangle. They are similar triangles because they have the same angles, alpha over 2 here and beta over 2 here. This line is an altitude in this triangle, and this line is the corresponding altitude in the other triangle. Therefore, this point corresponds to this point in the similar triangles, which means that the ratio n divided by m corresponds to the ratio p divided by q. And since ratios are preserved in the similar triangles, we get that n divided by m equals p divided by q as desired.